Hello, today we'll be talking about Lab 1 of constant velocity, so let's jump right in. So for an introduction, the purpose of this experiment is going to be to evaluate the accuracy of a computational model in predicting velocity, and we'll be using position to calculate displacement of velocity to see how fast the object is going and the direction the object is going in, and the force because it's going to be affecting the other two. And for our results, we're going to see that the program is going to need improvement as the margin of error was pretty high. So for our methodology, the process included first taking a video of an object, then using that video to give values in tracker and develop graphs. Then we'll use the tracker to develop a computational model, and we will finally compare the computational model with the tracker. So how was the tracker developed? Well, first of all, in pink, we have the X and Y axis, positive X going towards the right, positive Y going up. Then we have a calibration stick so that our computer knows the scale of our model. And in our experiment, this blue line is gonna be 10 centimeters. And then we have these points, which is gonna be where our object was at a given time step, which is a little inaccurate, and we'll see later why. And so how was the code developed? Well, first we're gonna set up some variables. First, ball position and ball velocity. The ball position is gonna be at the origin to make our lives easier. And the velocity is gonna be found using the formula v average equals v final minus v initial over 2. V final and v initial taken from 2 points from the tracker. And we're also gonna have time because it's gonna be affecting position. We're also gonna have the net force is gonna equal 0, and we'll see later why. And we're gonna have the final velocity equals initial velocity because the f net part of the equation is gonna equal 0, so it can just be cancelled out. And the ball position is gonna be taken using the formula final position equals initial position plus average velocity times delta time. For our results, we'll see the graphs look similar, but there's a little margin of error at the start being 0.01 meters, and at the end it's already getting at 0.05 meters. And so to talk about these errors, the first that we see is that the graph in the tracker is much more slanted than the one in the computer model. So you can see in the point 1.5, 0.20 in the tracker, our slope is below that point, but in the computational model it is above. And that's going to be because of friction and air resistance affecting the real live object, but it's not taken into consideration in the computational model. Then we also have that our y graph is going to appear as a mess. And this is going to be because of the earlier dots that weren't placed exactly in the axis. This is because of human error. We see that some points are above the axis and others are below. But this graph should just be aligned because there's no forces acting in y, as we see in the computational model, where there are no peaks nor drops because the velocity is constant. So for some questions, what if the axes were flipped? What will happen then? So just as a reminder, this is our original graph. If the negative x and positive y axes were flipped, then our graph will be decreasing instead of increasing because the object will be moving in towards the negative direction. If the x and y axes were flipped, then our x graph will be the one that we had earlier for y, because now the object will be moving in the y direction instead of the x direction. And so what does it mean that our net force equals 0? We use net force as 0 because friction and air resistance are neglected because time steps were too small, and After the initial push of the object, there was no other force, so according to Newton's first law, the object is going to want to stay in motion. So in conclusion, although the computational model could predict the motion to some degree, it was not accurate enough due to the absence of friction and air resistance. Thank you.